Right. So we were saying that around this area, okay, what you observe is that around this area there is literally no change in pH. Why is there no change in pH despite that we are adding hydroxide ions? The reason is that there is enough of the acid that neutralizes the incoming base. Okay, there is enough, 10% is enough to neutralize. If it's less than 10%, then it will not be able to neutralize the incoming base. If we were to add an acid, still the pH will not change much because there is enough base to neutralize the incoming acid. Okay, so in this region we say that acetic acid is acting as a buffer. Okay, in that region it is acting as a buffer. Around this area there is no change in pH. Okay, around what area? Around the pKa. At pKa, the amount of the acid and the amount of the base are the same. Therefore, they are able to neutralize incoming base or incoming acid. Okay, we call this point an inflection point. Inflection point. Inflection point. At the inflection point, the amount of acid is equal to the conjugate base. At that point, this mixture is acting as a buffer at maximum capacity. Okay. Now, what is a buffer before we proceed? A buffer can be said to be a homogeneous mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid that resists change, in pH when change in pH when small amounts of acid or base are added to it. Okay. So the full definition is that it's of course a homogeneous mixture of a weak acid is missing there, of a weak acid and its conjugate base, or a weak base and its conjugate acid that resists pH, that resists change in pH when small amounts of the acid or the base are added to it. In other words, a buffer maintains the pH near constant. It keeps it at a steady level. There may be minor changes, but generally speaking, the value of the pH is maintained. So here we are saying the pH is maintained around 4.76. Okay, around this area, the pH of this solution, this mixture containing acetic acid and acetate ion, is maintained around 4.76. Okay, if the pH is 1 unit less than the pKa, still the pH does not change much. Okay, If the pH is around 1 unit above, again the pH is maintained near constant. Okay, so that is how we define a buffer. So if you look at this titration curve, this part is a titration curve. If you look at the titration curve, this one, the one I've circled, is called the buffering region of the acid. The buffering region of the acid is between, okay, 1 minus and 1 plus pKa. Okay, so we can say minus plus 1 pKa. Okay, when you have 1 unit less than pKa or 1 unit above pKa, that region is called the buffering region. Okay, the ability of a buffer to resist change in pH is called its buffering capacity. Okay, is called its buffering capacity. What is buffering capacity? The buffering capacity is the ability of a buffer to resist change in pH. Put differently, the buffering capacity is the amount of acid or base that can be added to a buffer to change the pH, to cause a change of pH of 1. A change of pH of 1. Okay? The amount of acid or the amount of base, that is the number of moles of acid or the number of moles of a base that will be added to a buffer to change the pH by 1. That is a buffering capacity. Okay? The buffering capacity is maximum. Okay, the buffering capacity is maximum when pH is equal to pKa. Okay, the buffering capacity is maximum when pH is equal to the pKa of the solution. When the buffer has a pH that is equivalent to the pKa of the buffer, then you're going to have optimal buffering capacity. Okay. However, the buffer can still work. The buffer can still work when pH is equal to plus or minus 1 pKa. It's still effective. Okay. Still, this will be an effective buffer. Okay. Optimum buffering capacity is when pH is equal to pKa. Okay, the buffer still remains effective if pH is 1 unit above or 1 unit below the pKa. When you have the pH that is 2 units above pKa or 2 units below pKa, then the buffering capacity ceases to work. Okay. The buffering capacity will be overwhelmed by the acid or base that is added. In other words, either the amount of a base to neutralize the acid is not enough, or the amount of the acid to neutralize incoming base is not enough. Okay, so when you look at the titration curve, what can you deduce from the titration curve? Okay, there are a number of things that we can deduce from the titration curve. The number of things that we can get from the titration curve. Okay? Firstly, it can give us the quantitative value. Quantitative value of the extent of dissociation. Okay? In other words, it can give us the pKa. Okay? From the titration curve, we can get the quantitative value of the extent of dissociation of the acid, which is the pKa. 2, from the titration curve, we can also get the region in which the buffer is effective. Okay, we can get the buffering region. Okay, we can get the buffering region. Then we can also get, we can deduce whether the acid is monoprotic or diprotic or triprotic. Okay, it can give us the basicity of the acid. Okay, how do you get the basicity? If you have one inflection point, then the acid is monoprotic. If you have 2 inflection points, then it is diprotic. If you have 3 inflection points, then it is triprotic. Okay, so from the titration curve, we can deduce whether an acid is monoprotic or diprotic or triprotic. Basically, the number of inflection points reflects what type of basicity it is. If it's just 1, it's monobasic. If there are 2, they are dibasic. If there are 3, tribasic, as it were. Okay, right. Okay, so basically, that's what we can get, some of the things that we can get from the, not the only ones, but some of the things that we can get from the titration curve. Okay, so I looked at acetic acid. Let's look at say phosphoric acid. Let's look at the titration curve of phosphoric acid. Okay. So ideally, if you look at phosphoric acid, okay, look at phosphoric acid. This is your phosphoric acid. Okay, phosphoric acid does dissociate. Once it dissociates, it produces hydrogen ions, and of course, it produces it loses 1 proton. Okay, to the minus. Okay, this can also dissociate, losing 1 proton, okay, remaining with 1 proton. Okay, finally, this can dissociate also, losing the last proton that it has and forming phosphate ions, -2. Okay. So we can see that phosphoric acid is the triprotic. It loses the first proton, the second proton, and the third proton. So it is triprotic. Okay, meaning that if we did the titration curve of phosphoric acid, we're going to have 3 inflection points. 1 for the first dissociation, 2nd for the 2nd dissociation, the 3rd for the 3rd dissociation. Okay. Since we have 3 inflection points, remember inflection points relate to, what does it relate to? The dissociation constant. It relates to the pKa. So we could say that this is pKa 1, and this is pKa 2, and this is pKa 3. And these have been found, pKa1 has been found to be 2.15, pK2 has been found to be 7.2, pKa3 has been found to be 12.4. Okay? So, if it is tribasic, or if it is triprotic, it means that the equivalent points will be 3. 3 equivalent points. So we're going to say 1, 2, 3. 3, 2, 1. You want to be half here. 0.5 is 1.5, and this is 2.5. Okay. Right. So right. So let me have my 2 here, my 4 there, my 6 there, my 8 there, my 10 there, my 12 there, my 14. This is pH. This is equivalent volume. Equivalent volume. Okay. So if I started titrating, what I'll see is that there will be a sudden change in pH, and then it stabilizes, stops increasing, and then starts increasing. Okay, starts increasing, and then gradually starts being constant, and then starts increasing. It starts being constant, and then like that. So what you have is this titration curve for phosphoric acid. Okay, so you have 2 inflection points. This one, you have another one here, and another one there. Okay, draw this properly. Okay. Right. So this the value of pH here, which will be our 2.15. Value of our pH here should be our 7.2. Value of our pH here, this would be our 12.4. Okay, so this would be your pKa3